Hello students, today our topic of discussion will be the polynomials over binary field. In the last 3 modules we were concentrating in the Galois field mathematics, and we were trying to learn the different terms called the field, the ring and polynomials, the polynomial ring, and we could not now we will learn how actually the all those terms are related in the context of our spectrum communications, and all these terms that will be heavily related in the code generation of a code generation of data sequence spread spectrum as well as the frequency hopping spread spectrum communication systems. As we understand that codes are the heart of this kind of communication system design. So, it is really we need to have at least some basic idea how those codes generation process is heavily related with the Galois field mathematics. Basically these are the polynomials. So, where actually we will find there is a very deep understanding between the generated code sequence as well as a feedback circuit and the feedback input you are giving to the initial stages. And let us see how far we can proceed over the polynomials over the binary field concept, and how far we can relate these polynomials in the generation process of the different codes. Polynomials. The polynomials allow a very compact description between the generated code sequence of a linear feedback shift register with its feedback coefficients and the initial states that we set for the m stage memories. Hope you will remember that long back we were discussing about the linear feedback shift registers, which is a very fundamental block of generating the pseudo random sequences, the PN sequences. We also saw that there are different kind of the structures, and some of them are also matched filter based structure, and we also saw the derivations of how the output bits can be generated through that structure. We understood the periodicity of the generated codes. We understood what is how the feedback circuit needs to be designed, how the feedback to the initial stage needs to be given, how the stored data in the stages slowly proceed from the leftmost to the rightmost based on the clock pulse arrival, and we also understood the periodicity of the generated codes. So, in a linear feedback shift register, this output sequence what we have already generated in the last classes, those output sequences are having some deep relation, the way the feedback logic is designed and the way the initial states are given. So, polynomials are the bridge up compact description, I should say, who will show us the dependence of this output generated sequence with the feedback coefficients as well as with the initial state. That is why we are so interested about the polynomials, and as we are dealing with the Galois field too, because all the stage values that are stored inside the linear feedback shift register, they belong to the value of either 0 or 1. They are basically the elements of the belongs to the Galois field. They are basically the elements that belong to the Galois field too. So, the polynomial today whatever we will be discussing, that is the polynomial over Galois field 2. Any polynomial in the Galois field 2 in general can be written as f x, f 0 plus f 1 x plus f 2 x square dot f n x to the power n, where the term f 0, f 1, f 2 dot f n, we call them the coefficients. the x introduced here are called interdeterminate, and this interdeterminate are introduced for for the convenience in the calculation. See that there is a term called degree of polynomial. The degree is the highest order of x, provided that its coefficient value is non-zero. So, the highest coefficient if the highest order of x, or the highest degree of the x, highest power of x, I should say the power of x, where actually the non-zero coefficients are belonging, those powers are called, that highest power is called the degree of the corresponding polynomial. So, these are the terms this degree will be repeatedly called, because there are several relation of this degree with the generation polynomial and the generation function and the corresponding generating function, as well as the characteristic polynomial, and degree will play repeatedly degree will be called to define several characteristics of the generated polynomial in Galois field 2 in the context of linear feedback shift register. Now, let us consider that we have two polynomials, one is f x and another is g x. Let us also consider that both f x and g x, they belong to the Galois field 2. Let us also assume that the degree associated with f x is equal to n 1 and the degree associated with g x is equal to n 2. Now, given this situation, we will be interested to know how the expression will look like if we add these two polynomial and if we multiply these two polynomial. For addition, we write that f x plus g x will be given by the modulo 2 operation going on the bit by bit, and that can go, the addition will run with the maximum degree of n 1 comma n 2. Max n 1 comma n 2 says up to the largest value, whoever is the larger one, the summation will go up to that. If n 1 is the larger than n 2, the sum will go up to n 2 or vice versa. And this inner summation, to understand actually how does it go, in the next slide we will take an example to have a clear idea about the summation of two polynomials over Galois field 2. Here is the example. Let us have one f x, suppose be 1 plus x square of plus x to the power cube, who is having the degree of equal to 3, and this is my another polynomial g x with the maximum polynomial value is equal to 4, n value is equal to 4, degree of equal to 4. If we add these two, as I described in the last slide, that this addition is on a Galois field is a modulo 2 operation going on. So, hence it is an XOR operation. If 1 plus 1, it will yield 0, x 2 plus x 2 will yield 0, and you will be left with the terms called x 3 and plus x 4. Hence, the addition of x x plus g x in this example will yield the result x 3 plus x 4. The product, we will start again with the same two polynomials f x and g x, both belong to the Galois field 2, and one is having the polynomial degree n 1, another is having the degree n 2. If we multiply these two polynomial, the multiplication will be governed by the equation written in 1.48. Here this inner multiplication, this inner summation is basically a modulo 2 operation going on. Remember, unlike the addition of two polynomials, here the outer summation for over I will be going with the sum of both the orders, for sum of both the degrees n 1 plus n 2. It is not the maximum of n 1 and n 2, it will go up to the summation of n 1 plus n 2. We will take again another example, the 1 plus x 2 plus x 3 and 1 plus x 2 plus x 4, like our earlier case. If you keep on multiplying, so 1 multiplied by 1 will give you 1. You will generate actually 1 x squared term here, another x square term because of the multiplication of these two terms, and because of the summation operation with the modulo 2 operation going on, that will boils down to 0, that will boil down to 0, and you will be having the term independent term of x 3. For x 4, I will have another one x 4 term here, another x 4 term will be generated by the multiplication of x square with x square, and addition modulo 2 operation of these two x 4 term will lead us to 0. So, hence going by this pattern, these are the independent terms which will be left with x to the power 6, x to the power 7, 5, 6 and 7, and this is the result of the multiplication of two polynomials. You can easily verify that the rule of association, it is the associative, commutative and distributive laws, all the three laws they apply heavily over this multiplication as well as the addition operation of two polynomials over Galois field 2. So, this is a very important property, that if you are having a polynomial for Galois field 2, addition of two polynomials and the multiplication of two polynomials over the field will always follow the associative, commutative and distributive laws. Now, we come to a point which is called a characteristic polynomial. Characteristic polynomial is such a polynomial which always helps to give the equation of generating polynomial of a typical code. We will see how does it go. For our linear feedback shift register, which is having a stage of m, the characteristic polynomial is given as 1 plus sum of all the stages where the inside the summation there is a multiplication term of C I into x to the power I. C I, we understand that these are all the feedback switches that we have earlier discussed. The value of the C I equal to 1 signifies that this typical stage is contributing, output of that typical stage is contributing in the feedback process, otherwise it is not. If its value equal to 0 means it is not, that typical stage is not contributing to the feedback logic. And definitely we have also discussed earlier that the value of C m, if it is 1, it should be 1, such that the last stage, the mth stage of the feedback shift register contribute to the feedback logic. If it is not equal to 1, then that structure in the last stage will not have any contribution, and then the last stage will simply give one delay, we simply give one delay of the generated sequence by m minus 1 stages. Given this characteristic polynomial, now we would look into the generating function. The generating function of a linear feedback shift register is given by g x. It is directly related with the output. So, output is the A I is the output, which is directly the output coming from the stage S m I, and he is actually getting the summation of the outputs that is coming from the last stage over the clock pulses that is running from I equal to 0 to the very high infinity value. So, continuously the sequence is getting generated. We understand that this output A I is having a linear recurrence relation given by the fact that C k into A I minus k from this sum over k is equal to 1 to the stage number m can generate my output sequence A I. This equation we have established earlier when we are discussing the linear feedback shift register architecture. Remember, this expression holds good if and only if the clock pulse value exceeds the number of the stages involved in the linear feedback shift register. For I less than equal to m minus for I less than equal to m less than m, that means up to m minus 1, you will get only the output coming equal to the initial stage values stored, inside the stages. So, recap having the remembrance of that fact, we understand that this expression I is equal to 0 to infinity is basically having two components. The situation 1, when the value of I is varying between 0 to m minus 1, where m is the number of the stages. Another stage, this process number 2, where I is having the value from m to infinity. So, the value of a I for both the cases are not same. For I equal to 0 to m minus 1, it is directly whatever actually you have stored in the initial stage given by the expression a I x to the power I. But once you are crossing that value m minus 1 from m to infinity, he will be governed by the a I will be substituted by this expression. So, we have just broken this initial generating function by this expression. Now, if I change the order of the summation here, I will be ending up with c k and x k I have taken out. So, this will go x, if I take x k out, then that guy will be x a I minus k, and it will be x I minus k also. Please check that this will be not x I, it will be x I minus k. Now, if I try to see this expression which is written inside, then this is basically I can rewrite in the form of this g x if I include the term which are coming in between 0 to m, and here I is not exactly I, it is equal to I minus k. So, if I substitute that, it will go up to m minus k minus 1, and all those guys will come down to a I to x to the power I is varying from 0 to this zone. So, this is a classic equation that we are ending up here with 1.52, where this is a generating function who will finally help us to generate the final code sequences. Now, if I take the expression, if I club this expression of the generating function with that of the initial f x characteristic polynomial we have discussed here, and if I take the multiplication of this g x and f x, we will lead here, and with some simple mathematical calculation and derivation, we will come down to this value, where actually finally this g x, this generating function, it will be equivalent to this when this j is replaced by I, it will be given by this expression divided by f x. While deriving this expression, you have to consider that the c 0 is equal to 1 initially, and c 0 is 1 in the throughout the expression. And as I told already mentioned that this j is replaced by I, and so hence these two are the similar kind of expression that we are getting, and this x I is taken out. So, your expression will look like the generating function in terms of the characteristic polynomial is given by 1.54. Now, the key part and the key learning from this expression is, see if I get the numerator of this generating function is nothing but another polynomial, say phi x, and if we consider that, and then the generating function can be written like g x equal to phi x divided by f x. It is the indication basically that linear feedback shift register sequence, the output sequence can be generated by the characteristic polynomial f x, and the degree to do that, the degree of this phi x should be less than the degree of this f x. This output sequence that can be generated by f x, if actually generating function means characteristic polynomial actually can generate the generating function if you know f x, that is one point. And to do that, actually there should be the existence of another polynomial, where this polynomial will be completely divisible by this f x in such a way that the degree of that polynomial is having at least less than 1 degree than that of f x. Now, this equation that we have shown in the last slide 1.54, it clearly indicates what? It clearly indicates that the generating function or the generating function which is generating the output as well, he is completely describable by your CK values, that means the feedback coefficient logic and also the initial conditions that are coming up. And we will take a good example to find out how does it go with a practical example. In this figure, let us consider a figure where we are having 3 stages of to generate the linear feedback shift register. Clocks are driving the stages and the C1 is equal to 0. So, he is not contributing to the feedback logic, but C2 and C3 are on equal to 1, and so this is the XOR logic only in the feedback path, where actually the contribution from the output of the two stage number 2 and stage number 3, they are logically combined to give the feedback to the stage number 1. We understand that if we follow the equation of f x given in the given here. So, my value of the C1 is equal to 0. So, x to the power 1 is also not existing. For the next two C2 and x squared, it will be a term. So, C2 is equal to 1. So, the term will be x square, and the C3 also C1 C3 is equal to 1 and x to the power q. So, I will be ending up with for f x equal to 1 plus x square plus x 3, which is exactly coming in the denominator here. So, the generating function will be given by, similarly you can find out the value of the phi x following the equation number 1.54, you substitute there, and this is coming from the expression of this characteristic function f x, which is given by 1 plus your equation that is written earlier. C k and C I into x to the power I is moving from 0 to infinity. So, where I is moving from 0 to infinity. So, like this actually, now if I divide these two polynomial, now the generating function will be obviously known to us. So, the key understanding is that you need to find out the characteristic polynomial over a Galois field to understand that what will be the generating function for a typical kind of the code that we are trying to generate. So, generating function and the characteristic polynomial, they are the two parts, they are the key essential and the true essential parts of code generation for your space vector communication system. Now, let us go ahead with few more characteristics of these polynomials that we are discussing now over the binary field. Suppose there is a polynomial called p x. The p x is said to divide another polynomial b x. Remember, p x and b x both are belonging to the same field, and p x is said to divide b x if and only if there exists another polynomial h x on the same field, such that the b x is equal to h x into p x. So, we understood about the addition of two polynomials over the field, multiplication of two polynomials over the field. This is the condition of division of the two polynomials. Now, think a situation that if a polynomial p x over this Galois field 2 is having a degree of m, then he is said to be irreducible if and only if it is not divisible by any other polynomial who is having some degree less than small m, but greater than 0. So, why we are so interested about the irreducible polynomial? Because we will see that it has some connection later on with the primitive polynomial. So, it is required to understand what is the meaning of irreducible polynomial. I repeat, if a polynomial is having a degree of small m, and if it is not divisible by any other polynomial over the same field who is having a degree less than small m, but greater than 0, then we will declare that P x is a primitive polynomial. It is not irreducible. If it is irreducible over a Galois field 2, then it is obvious that if P x is irreducible, then it is obvious that for P 0 is not equal to 0, otherwise that x would have divided this P x, right. So, for example, if P x, we find that it has an even number of the terms, then the P 1 which is equal to 0, these are the fundamental theorem of the algebra shows that x plus 1 should also divide P x, because P x is at least one even number is there. So, it is not the x, it is the x plus 1 should divide P x. Another important consideration, that if P x is having an odd number of the terms, then an irreducible polynomial Galois field should have always an odd number of the terms always by default, because if it is having an even number of the terms, then x plus 1 will divide that polynomial. But remember that it is not a sufficient condition to prove the irreducibility. Here is an example, suppose 1 plus x square, they are having the odd number of the terms, but it is irreducible, fine. But there is another polynomial 1 plus x to the power 5. We cannot see that, we cannot declare that as it is having a odd number of the terms. So, it is irreducible, because this polynomial is reducible by these two other polynomials. Hence, by just checking the polynomial is having odd number of the terms, we cannot declare that it is irreducible. But if a polynomial is irreducible, definitely you will end up with a conclusion that it is containing the odd number of the terms. Now, next if I am having a shift register sequence A I which is periodic and which is having a period of n, then this generating function that we have just now learnt, which is a form of phi x by f x, where f x is the characteristic polynomial, that we can be expressed like this, where actually this g x plus g n x to the power n g x plus x to the power 2 n g x, these are the combination of all this, and where this, hence it can be written as this g x summation of all this x to the power I n, I is going from 0 to infinity. And what is this? This is nothing, a series of 1 by x to the power 1 plus x to the power n, 1 by 1 plus x to the power n. Now, if g x is having where this g x, its polynomial should have a degree of n minus 1 obviously. Therefore, if I write down this expression in terms of your and substitute its value from here, then what we will end up with is this is equal to my phi x by f x, and so small g x will be is equal to nothing but my phi x into 1 plus x to the power n by f x. This is another important conclusion in the context of the code design. What does it mean? You know that see, if f x and phi x, there is no greatest common divisor between these two polynomials, and which is obvious not to have, because your phi x is having degree less than the f x. So, you may not be able to find a greatest common divisor between phi x and f x. If you do not find it, then in order to hold this equation, it should happen that f x should divide 1 plus x to the power n. So, with this understanding, when f x is dividing my 1 plus x to the power n, then there must be there must exist another kind of the polynomial over the same Galois field too, say its value is h x, and such that this f x into h x will now be equal to 1 plus x to the power n, right. So, if I substitute this value here on the phi x by f x, where this f x is now is equal to my 1 plus x to the power n by h x, and we are ending up with another very nice expression that the generating polynomial will be given by phi x into h x divided by always 1 plus x to the power n. So, thus this characteristic polynomial f x, it generates a sequence who is having a period n for all the kind of the phi x, and hence all initial states also it will keep on creating that. Now, a polynomial we is over the Galois field 2 having a degree m, we will call it a primitive polynomial. For what? If when the smallest positive integer for which it is the polynomial divides this 1 plus x to the power n is given by n is equal to 2 to the power m minus 1. So, what I said, repeat. So, a polynomial, suppose there exists a polynomial over Galois field 2 who is having a degree of small m, and this polynomial has a smallest positive integer n for which it is dividing this 1 plus x to the power n in such a way that this value of n is related to the degree of the polynomial by this relation. Okay. If this happens, then we call that this polynomial is a primitive polynomial. Now, remember one thing, a primitive characteristic polynomial, it is not a primitive polynomial only, it is a primitive characteristic polynomial also, because this is a characteristic polynomial who is dividing 1 plus x to the power n. So, this primitive characteristic polynomial of this degree m, so it can now generate also a sequence who is having a period of small n or equivalent to period of 2 to the power m minus 1. But we understand that characteristic polynomial who is generating 2 to the power m minus 1 sequence, that sequence should be a maximal length sequence, and that polynomial who generates the maximal length sequence, that characteristic polynomial always have a degree is equal to small m. Okay, so, it is just opposite proof that a ML sequence, the characteristic polynomial who generates an ML sequence always is a primitive characteristic polynomial. Okay. Now, suppose to prove whether these primitive polynomials are reducible or not, in order to check that, let us consider that the polynomial of the positive degree m can be factorized, and so hence this f x is equal to given by f 1 into f 2, f 1 x into f 2 x. Suppose the degree of this f 1 x is equal to m 1 and the degree of f 2 x is equal to, of course, m minus small m minus m 1, because total degree is equal to m. If I do the partial fraction expansion, then it yields that 1 by f x will have something called a x by f 1 x plus b x by f 1 x, and they can serve as, both of them serve as the characteristic polynomials individually. So, hence the period of this first term of this expansion can never have actually a period which goes beyond 2 to the power m minus 1, and whereas for the second case it can never have a period that exceeds more than 2 to the power m minus m1 minus 1, because both of them are characteristic polynomial and they are supposed to generate a period which is equal to 2 to the power their corresponding 2 to the power m, which is the corresponding degree of them minus 1. Here one is having the degree of m1, another is having degree of m minus m1. So, actually the generated sequence can never have a period more than this. And so, in therefore, the period of 1 by f x cannot exceed this value. So, if it cannot exceed this value, so it contradicts with the assumption that it is a primitive, because if it is supposed to be the primitive, then its value m should be is equal to its primitive, then its order m, then its period n, generated sequence period n, it should have actually 2 to the power m minus 1. or the value, the degree of the characteristic 1 plus x to the power n, that n should have a relation with 2 to the power m minus 1, which is not holds good, which is does not hold good, which is not holding good here. If it does not hold good here, then what the conclusion is, the conclusion that the assumption that we did that it can be factorized is wrong. Hence, the final decision is that a primitive characteristic polynomial is always irreducible.